Pulse modulation. That is, the definition for pulse modulation is the characteristics or parameters of a pulse carrier is varied in accordance with the amplitude of the analog message signal. The types of pulse modulation will divided into analog pulse modulation and digital pulse modulation. So the analog pulse modulation is again divided into PAM and PTM, pulse amplitude modulation and pulse time modulation. Again, this PTM will divide into two types, that is pulse width modulation and pulse position modulation. Then the digital pulse modulation have a types, that is PCM, pulse code modulation, then delta modulation and adaptive delta modulation and differential pulse code modulation. Then the analog pulse modulation. This analog pulse modulation is a technique in which each sample of the analog message signal systematically changes the characteristics of a pulse carrier, that is amplitude, width, position. Then this analog pulse modulation will classify into three types, that is pulse amplitude modulation, pulse width modulation and pulse position modulation. Then sampling. Sampling means formatting an analog signal proceeds in three types, that is discretization in time, which is known as by the name of sampling, and discretization in amplitude, which is known as quantization, and encoding means the encoding the quantized values. So generally sampling means the sampling discretifies an analog signal in time domain, so that instead of a continuous time waveform, we get a continuous values of the signal at the discrete points of time. That means the analog signal is converted into a discrete time signal. Generally we can have a definition for sampling is analog signal will convert it into a discrete time signal. So what is meant sampling theorem? That is, the analog signal m of t will apply into a sampler. We can have a discrete time signal, that is ms of t at the output side. So the statement of sampling theorem, first one, a band limited signal of finite energy which has no frequency component higher than w hertz, completely described by specifying the values of time separated by 1 divided by 2w seconds, that is t is less than or equal to 1 divided by 2w seconds. This is the first statement. Then the second statement is a band limited signal of a finite energy which has no frequency components higher than w hertz, completely maybe completely fully completely or maybe completely recovered from a knowledge of samples that were taken at the rate of 2w samples per second. This is the second statement of sampling theorem. So that means the highest rate of sampling will give the minimum sampling frequency needed to reconstruct the analog signal from the sampled waveform. We can have a sampled waveform, again we can reconstruct the original analog signal, that is fs greater than or equal to 2w. At that condition only we can have a reconstruction signal. So where here fs, that is sampling frequency, w is maximum frequency of the input. Then the Nyquist interval is reciprocal of the Nyquist rate. So that means Nyquist interval is the reciprocal form of Nyquist rate, that is 1 divided by fs. Then the time interval between two adjacent samples is also said to be a Nyquist interval. Then we can have a proof of this sampling theorem. So first, impulse or instantaneous or idle sampling. In that condition we have two parts and three parts. That is, first one, a representation of g of t in terms of its samples. Second one, reconstruction of g of t from its samples. Then the representation of g of t in terms of its samples, we can have 3 steps. So first we define the sampled version of g of t. Example, g sigma of t. Then find the Fourier transform of g sigma of t, that is g del of f. Then the third step, find the relationship between g of f and g del of f. These are the methods to find the proof of the sampling theorem. In the types of sampling, that is we have the 3 types of sampling. So first one instantaneous sampling, second one flat earth sampling, third one natural sampling. So instantaneous sampling means the instantaneous sampling is also called as an ideal sampling or impulse sampling, because an analog signal m of t is sampled by a sequence of unit impulse or Dirac delta function. Second, the natural sampling, an analog signal m of t is sampled by a flat of rectangular pulses with finite width. The top of each pulse in the sampled signal retains the shape of the original signal. Then flat of sampling means an analog signal m of t is sampled by a flat of rectangular pulses. The top of each pulse is in the sampled signal is flat. These are the 3 types of sampling. So we have a signals, that is input signal. We can have a sine signal for impulse and natural flat of sampling. Second, the carrier signal in the pulse chain form. Third one, the sampled signal. So first one impulse sampling, second one the natural sampling, and third one flat up sampling. So in this flat up sampling, we have a flat at the top of each pulse, and here natural sampling, directly the pulse carrier is fixed in the message signal. So and impulse signal, so we have a impulse response signal at each sampling output.